All right, so as what I am saying a while ago, we are going to expand the sine function. Can you still recall how to expand the sine function? So you will rewrite the Laplace transform and then expand the sine function. That will become sine of t multiplied by cosine pi minus cosine of t multiplied by sine of pi. Take note of the values of cosine pi and sine phi. Can you still recall the values of sine pi? Oh yes, that becomes 0 for cosine pi, that is negative 1. Now, if we are going to substitute the values, the result would be e raised to sine, the Laplace transform of e raised to negative of sine e raised to t multiplied by sine of t. Now, this Laplace transform is easier to solve. This is just your first shifting theorem. So in your first shifting theorem, all you have to do is to take the Laplace transform of sine. That will become 1 all over s squared plus 1. And then we are going to change s equals to s minus 1. So your final answer would be negative 1 all over s minus 1 quantity squared plus 1. That's how you solve the second shifting theorem. If for our solution number 2, no, same problem, but we are going to solve this using another method. Okay, for another method, we are going to manipulate the exponential function so that it will have minus pi, same as the angle inside your sine function. So how are we going to manipulate that? We are going to subtract the exponent of e by pi, and we are going to add that by pi. Now, negative pi plus pi is just 0, so it does not have an effect to your e raised to t. So what are we going to do next is to separate e raised to pi. So by taking out e raised to pi, that will become e raised to pi multiplied by e raised to t minus pi multiplied by sine of t minus pi. Take note, the function of the exponential function, no, and the sine function have the same amount of shift. And in fact, e raised to pi is just a constant term. So for the constant term, we are going to put that outside your inverse your Laplace transform sign. So what will be left here will be e raised to t minus pi multiplied by sine t minus pi. So in this case, we can solve for the value of a. So now a here by inspection, that is just equal to 1. A is just equal to 1. And what about the function of t minus pi? Of course, the function of t minus pi is just equal to e raised to t minus pi multiplied by sine of t minus pi. So if you have that function, if we will remove the amount of shift in your function of t minus pi, that will result to e raised to t multiplied by sine t. That will be your function of f. Now, to solve for function of s, we need to take the Laplace transform of your function of t. So that becomes the Laplace transform of sine is 1 over s squared plus 1. And then you have e raised to t, that is the first shifting theorem. So we will shift s now by s minus 1. So your final answer would be, for your fs will be 1 all over s minus 1 quantity squared plus 1. So we have the value of a and we have the value of fs. Now, we need to put that in your, the value of s will be equal to e raised to pi times the Laplace transform of a certain value. What's that? What's the Laplace transform that? Okay, that is the Laplace transform of e raised to, that's the Laplace transform e raised to t minus pi multiplied by sine of t minus pi. Now, the Laplace transform of that can be solved using the second shifting theorem. Now, if you will substitute a, no, to your e raised to as, that becomes e raised to pi multiplied by e raised to minus pi s multiplied by 1 all over s minus 1. Okay. 1 all over s minus 1 quantity squared plus 1. Right. Now, let's proceed. Let's proceed with our next, with the final answer. So your final answer would be e raised to minus pi s plus pi multiplied by 1 all over s minus 1 quantity squared plus 1. That would be your final answer. All right. Now, let's move on to our next example. So our next example, oh, this is not an example, but this is our new topic for today. So our new topic for today is about the Laplace transform of the derivatives. So the Laplace transform of the derivative is simply written in mathematically as the Laplace transform of the derivative of y sub t is just equals to s. Take note, this is the first derivative. So for the first derivative, you are going to multiply s to your function of s. Take note, instead of writing f of t, I used y of t because later on in our application, we will be using y of t instead of f of t. So the Laplace transform of y of t is just y of s minus y0. Okay, that's the convention that we will be using. Now, for the Laplace transform of the second derivative of yt, that becomes, take note, for second derivative, s squared is multiplied to your y sub s minus s times y0 minus y prime 0. That will be the convention that we will be using. Okay, take note that y0 and y prime 0 are initial values. If they are not given, it is assumed to be 0. Okay, more of this will be discussed no, in our following meeting. Okay, if you can see my background, I'm in Kabatuan actually. No. At the back there, over there is the Iloilo International Airport. So all right, now let's proceed with our first example. Assuming, no, for our first example, let's say I have here, okay, let's have this view for a while. I have here the Laplace transform, the derivative of sine. Do you know what's the derivative of sine? Oh yes, that's cosine, right? So that is the same as taking the Laplace transform of cosine. But in this case, now we will be using the property of Laplace transform. Actually, no, the Laplace transformation of derivative is the continuation of the properties of Laplace transform. Okay, now let's take the Laplace transform of the derivative of sine. So since this is the first derivative, we are going to multiply s to the Laplace transform of sine. So sine there, s there is multiplied to the Laplace transform of sine, and we know that the Laplace transform of sine is just 1 all over s squared plus 1 multiplied by s. That becomes s all over s squared plus 1. Take note, s over s squared plus 1 is just the Laplace transform of cosine. Now, if you're going to take the derivative of sine first, that becomes cosine. The Laplace transform of cosine is s all over s squared plus 1. Okay, so you can take the derivative first and take the Laplace transform, or you may take the Laplace transform right away. All right, now let's have another example of the Laplace transform of derivatives. Now this time, we are going to solve the Laplace transform of the derivative of t multiplied by e raised to 2t. Now the Laplace transform of that will be s multiplied by the Laplace transform of t multiplied by e raised to 2t. I'm sorry, no, the text is not that clear. But that is t multiplied by e raised to 2t. So I need to change the color of that to red. That you will notice I'm using red as the color of my font so that it will be easily seen in your screen. If I use black, no, that is not clear to the screen. All right, now the Laplace transform of e raised to t times e raised to 2t is just the same as 1 over s squared. Take note, the Laplace transform of t is 1 over s squared, and this is the first shifting theorem. Now, for the first shifting theorem, you're going to change s to s minus 2 because um, your exponential function there is e raised to 2t, meaning to say you are going to shift the s domain by 2 units. So after substituting the values, we have s all over s minus 2 quantity squared. That is equal to s all over s minus 2 quantity squared. Okay, that is the Laplace transform of the derivative. Okay, let's have another one. This will be the last example in our Laplace transform of derivatives. Now, we have here the Laplace transform of e raised to 2t multiplied by sine of 4t. Now, if we will take the Laplace transform of that, that is just the same as s multiplied by the Laplace transform of e raised to 2t sine of 4t. Still, no, the Laplace transform is actually in the form of first shifting theorem. Now, it is easier for us to take the Laplace transform if we know the Laplace transform of sine 4t. That is 4 times 4 all over s squared plus 16. That is the Laplace transform of sine 4t, but you are going to shift the value of s by 2 units. So that is, simplifying it further, that will become 4 all over s minus 2 quantity squared plus 16, or to simplify it further, that will become 4s all over s minus 2 quantity squared plus 16. If you will notice, s there is not shifted because that is outside your Laplace transform. Okay. All right. Now we go to the Laplace transform of integrals. Okay. I am actually um, looking for an angle, best angle for my text to be seen. Oh, in this case, no, this I will be using this angle. Okay, let's try what is the principles of the Laplace transform of integral. So a while ago, we've discussed the Laplace transform derivative. So if that is the derivative, uh, s is multiplied. If that is the Laplace transform of integral, you're going to divide that by s. Okay, so the Laplace transform of integral is written as the Laplace transform of integral of yt dt with limits from 0 to t. That is simply 1 over s multiplied by y of s. Take note, I am using y instead of f. All right. Okay, I will take this angle. Now let's have an example here. Supposing I have here, so I think no, it is better if no, I will focus on the blue screen, okay, the sky. Okay, let's have this problem first. So the Laplace transform of the integral from 0 to t of sine t dt can be written as 1 over s multiplied by the Laplace transform of sine. Take note, y sub s there is the Laplace transform of sine, and we know that the Laplace transform of sine is just 1 all over s squared plus 1. So simplifying it further, that becomes 1 all over s cubed plus s. So this topic is not that difficult. All you have to do is to know the basics of Laplace transform. All right. Okay, let's have another problem in the Laplace transform of integrals. So let's have this problem. What is the Laplace transform of of the integral of e raised to minus 3t cosine t dt, now with limits from 0 to t? Now, take note of the formula above. So you can write this as 1 over s multiplied by the Laplace transform of e raised to minus 3t times cosine t. And the Laplace transform of e raised to minus 3t cosine t can be solved using your first shifting theorem. So that is, okay, take note of 1 over s. 1 over s is outside the bracket. So that will become s all over s squared plus 1. Okay, that is the Laplace transform of t. But we are going to shift s by s plus 3. So in that case, no, that becomes 1 over s multiplied by s plus 3 all over s plus 3 quantity squared plus 1. Simplifying it further, that becomes s plus 3 all over s all multiplied by s plus 3 quantity squared plus 1. All right, so that's the end of our presentation. I hope you've learned something in my topic for today. So I will be discussing next meeting the application of Laplace transform. So for now, so enjoy your online class and try to solve and learn to solve as many problems as needed by your course. Okay. So for more information, just message or comment on our. You can comment on our the link in the YouTube. Okay. That's all for now. See you next meeting.